All right, last topic. So some of this that we're going to be doing today in particular, but in others in this probability and statistics topic, we do bits of in methods as well. So you will have done some in methods of it. So certainly this first bit, discrete random variables, just a reminder, whole number values as outcomes. And then we represent probability distributions in this way, where X is our thing, and then how many times does it come up? None, one, twice, etc. And what's the probability of it coming up twice? All right, so done a bit of that in methods, as I've said. All right, so let's go down here and have a look. Here's an example that I've taken from your textbook. So the probability distribution of the number of cars Matt sells in a week is given by this here. So I suppose Matt is paid $7.50 each week plus 1,000 commission on each car. All right, so with this, he gets $7.50. That's how much he gets, whether he sells cars or not, and then he gets 1,000 each. So express Matt's weekly salary as a linear function of X. All right, so Matt's salary. So his salary, what does he get for his salary? I think about what I've just said there. He gets $750. Sometimes they call that a retainer. So $750 plus, plus what? Plus how many thousand for each car. All right, and function of X, and X is the cars. All right, so X is the cars, number of cars sold. So what can we write that? Oops, we don't need that. His salary then would be $750 plus 1,000 X. All right. So what is the probability distribution of S? So now we're going to change this from X to S. So this is numbers of cars sold. Now we're going to look at salary. All right, so because his salary relates to how many cars he sells, that now means that we need to look at his, we need to look at his salary. All right, and that's S. And so what is his salary? Well, if he doesn't sell any cars, he still gets $750. But if he sells one car, he gets his $750 plus another 1,000, which is 1,750. Then if he sells two cars, it's 2,750, and so on. And three cars, and I'm going to need four as well. So three cars, let me get rid of that. I'm going to need to squeeze it up because I need to squeeze in. So three cars, it's 3,750, and if he sells four cars in the whack, $4,750. And so the probability of each of those, that S is equal to little s, is exactly the same. All right, because all we've actually done is change this top line here from numbers of cars sold to actual salary, money you take home. And so the probability of how much money you take home depends on the cars you sell. So it depends on that probability. So it's 0.45 here, 0.25 here, 0.2, 0.08, and 0.02. All right. What is the probability Matt earns more than $2,000 in a week? All right, so That's C, the probability that the salary is greater than 2,000. All right, so that's 1,750. That's 2,750, so that's more than 2,000. So we're interested in those ones there. So we're interested in where it equals S equals 2,750 plus the probability X equals 3,750 plus the probability that S equals 4,750. All right, so 0.2 plus 0.08 plus 0.02, which would be 0.3. All right. So 30%. So in 10 weeks, 3 of those weeks, you would earn more than 2,000. All right. On average. All right. And we'll get to those details of statistics in terms of average and expected value in that in a bit. All right. So there's our discrete, our continuous. Left myself a page and didn't need it. Continuous random variables, so it can be any value. Oh, the thing that I didn't mention, discrete. You think about if you want to figure out if something's discrete and you've not got that table, think about, are you counting? If you say, can you count this thing? And the answer is yes, then it'll be discrete. Whereas continuous, you would say, do I measure this thing? If the answer is yes, then it's continuous. All right, so outcomes can have any value. Probability is given by what's called a probability density function, PDF. Where? And so these probability density functions, they can be any sort of function at all, but they must satisfy these two criteria. So got to be greater than or equal to 0. All right, so as it says there, you can't have a negative probability. All right, so if you've got a dice, 6-sided dice, normal one numbered 1 to 6, what's the probability of getting a 10? Well, that's 0. It's not negative, it's 0. So it's got to be greater than or equal to 0. And the other thing is that all the probabilities, and so if this is a function, all of the probabilities, when you add them all up, they've got to equal 1. All right, so it doesn't matter whether that's discrete or whether that's continuous, same thing. All can only add up to 1. So often, as I said here, any function can be used. So often that function will have a restricted domain, and that restricted domain will be there to ensure that when we work out the area in that restricted domain, we get a total of 1. All right, but again, we've done some more on that in specialist maths. Specialist maths. We're in specialist maths in methods. All right. Here we go. Where are we? Example 2 here. So here's our probability density function. So this one here is an x squared, so it's a bit of a parabola, for example. We've got a minus in front of there, so it's an upside down parabola. And what we're told here is there's two aspects of it. So it's 0 is less than or equal to x is less than or equal to 1. So in that domain, this is our probability density function. Outside that domain, so when x is greater than 1 or less than 0, the probability is 0. All right, so restricted domain on this parabola so that it fits into these two conditions. All right, so what do? Find the probability that x is less than 0.5. All right, so for A, probability that x is less than or equal, I should say, 0.5. Now with these, we are looking at less than or equal. As it turns out, for technical reasons, x less than 0.5 and x less than or equal to 0.5 is the same. But we don't need to worry about that. All right, so when x is less than 0.5, when we go back to here, here it says negative infinity to infinity, all right? So it's not always negative infinity to infinity that we actually need to look at. And the reason for that, I will try and explain here, is we really only need to look at this bit here from 0 to 0.5, because when it's less than 0, its probability is 0. So effectively, if you go back to negative infinity, when you're coming from negative infinity all the way up to 0, the area underneath that graph, well, there isn't any, it's equal to 0. So for convenience for us in less working, we only need to consider this top part, and we consider that domain. So what does that mean? That means that all we need to consider is 0, which is the bottom end of that domain, up to what we're interested in, which is 0.5. And our function is 1.5, 1 minus x squared, and dx. And we know how to do all of that stuff. So you can either do it by hand or you can get your calculator out and do it. And I've shown you how to do that in methods, so I'm not going to go and show you how to do that now. And then you get 0.6875 for that. All right, now it says let y be 2x plus 3. So y is some other thing, and it is twice this one plus 3, and we want to find the probability of y is less than or equal to 3.5. All right, so let's have a look at how we might approach. So we're going to, it would be part B. So here we go, part B. There we go, that's better. All right, so we've got y is equal to 2x plus 3. And we want to find the probability of y, so we're going to have to relate that back to x. All right, so if I rearrange this, y minus 3 is 2 lots of x. Divide by 2 both sides. And then we get that x would be equal to y minus 3 over 2. And so what we are after in the question, it says, is look at the probability of y is less than or equal to 3.5. All right, and so we're going to change that because x, which we know the probability of, is related to y in this way. So we're looking at a y value of 3.5. So the x value that we're looking at is 3.5 minus 3 over 2. 3.5 minus 3 is 0.5 over 2, which is 0.25. So what we're looking for then is that we can say that then the probability that y is less than or equal to 3.5 is the same as the probability that x is less than or equal to 0.25. And we know the probability density function for x, there it is here. And so we just do another integral. And so that is the integral from, again, the bottom end, the domain is 0, and we're going up to 0.25 of 1.5, 1 minus x squared dx, and again you can do it by hand or you can do it on the calculator, 0.3622. All right, so there's that one. Now next, excuse me, just grab a drink. Okay, so the next I've mentioned before about means and stuff, so here we go with that. So the mean of random variables. So in this context, as it says, and we've mentioned in methods, the mean is called the expected value. So what value would you expect over a long period of time? So there's two ways you can do it. So for discrete random variables, it's the sum of x times the probability. And for continuous, again, it's an integral. So the x times probability is the same part, but here we add up, because it's discrete, we add up all the individual ones. And here, because it's not discrete, we use the integral. All right. So in both cases, if x is a random variable and y is equal to ax plus b, and a and b are constants, then the expected value of y is related to the expected value of x in this way. Okay. And so there's proofs of all of that stuff on these 2 pages. You don't need to repeat the proofs. You only need to use the stuff. All right, so that's the mean, or the expected value. And now, of course, when you do something over time, you're not always going to get that value you expect. Sometimes you'll get something different. And so that's what we call the variance, how much it's varying from the mean or the expected value. All right, so variance, the measure of how far each number is from the mean, so how much it varies from the mean. Right, now I just need to clarify this a little bit here. So here it is. So for discrete, it's the sum of x squared times the probability minus the mean, and then you add those bits up. Now what I've got over here is for continuous, so that's for discrete. So for continuous is this, so it's a bit unclear. So for continuous random variables, it's related to this bit, which is x squared times fx dx, and again from negative infinity to infinity, minus the mean bit squared, and the mean bit is again negative infinity to infinity of x times fx dx, and I've squeezed that in again, and all squared. All right, so for continuous random variables, this is a version we can use. All right, now also there's if y and x are related in this way, then the variance is related like so. Again, we've done those in methods. All right, so proof of all of that stuff is page 595 in your textbook. And also just a note that sigma is the standard, I don't know why I put an E on the end there anyway, is the standard deviation, and the variance is the standard deviation squared. Again, something that we will be using. All right, so this one example here, continuous random variable x has a mean of 10 and a variance of 2. Find these things here. So the expectation of 2x plus 1. And so that's where we're using, what are we, expectation value. That's where we're using this here. 2x minus 1. So there we are. There it is there. Plus 1. Scroll back down. Hope you don't get a headache. So that's the same as twice the expectation value of x plus 1, which is twice times 10 plus 1, which is 21. And the variance, so that's the one up here. There it is. The variance of ax plus p, a squared times the variance of x. And so the a is the number in front of the x. And so there's the number in front of the x, and that's negative 3. So then it's negative 3 squared times the variance of x. So that's 9 times 2, which is 18. All right. So that's a couple of quick examples of those. All right, next, mean and variance of linear combination of two random variables. So there's more on this on pages 597 and 98. So if you want some proofs, that's where you can go. All right, so for random variables x and y and constants a and b, and so this is how we put them together. All right, so the expected value of ax plus by is related to the individual expectation values by that relationship. And so the variance is also by that relationship, provided x and y are independent. So that means that they don't affect each other. All right, let's have a look. Manufacturing process involves two stages. All right, so there's your x and your y, two separate things that you've got to put together to get your product. Time taken to complete the first stage, x hours, a continuous random variable with mean and standard deviation. All right, so I'm going to, over here, here's my x and here's my y. And so my mean is 4. My standard deviation is 1.5. So that means my variance would be that squared, which is 2.25. All right, the time taken to the second stage is y, continuous random variable, mean is 7, standard deviation is 1, and so that means our variance, y, not x, is 1 squared, which of course is 1. All right, find the mean and standard deviation of the total process. The times taken are independent. All right, so the mean, the expectation value of the whole process, is simply that of each individual process added. So 4 plus 7, so 11 would be the expected time to finish that process. Now there would be a variance on that, but we're actually asked for the standard deviation, which of course, remember, is the square root of the variance. And the relationships that we have to work with, these ones here, are about the variance. Okay, so the variance of x plus y, and because the numbers in front of here and here are 1, it's the same here over there, then it's just simply the variance of x plus the variance of y. All right, so I haven't all of a sudden come up with some different relationships. All right, so these numbers are 1 in the example. All right, so they are the same. So what do we get? Our variances is 2.25 and 1. Got to add them together. $3.25. And then we want the standard deviation. And of course, the standard deviation is the square root of the variance. So we're looking at the square root of 3.25, which when you get your calculator comes to 1.803. All right, so there's a bunch of stuff there. All right, so there's quite a long-ish kind of lesson, this one, getting into it. Right, so I don't want to spend too much time on this, because really, ultimately, so far, the basis stuff we've already done in methods. So it's just really applying it in it. I was giving you a background, but the applications here will be a little bit more complex than methods, i.e. that first example where we changed to how much the person earns. All right, anyway, I'm waffling. All right, the next one, a linear combination of independent normal random variables. All right, so now we're looking at this normal. So a normal random variable is one, when you graph it, you get this bell-shaped curve. All right, and that's used for all sorts of stuff. And the combination of independent normal random variables is the same as any two random variables. All right, so what I was just talking about previously is about random variables. All right, and so all of those things that we did before, blah, 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 waffle, waffle, waffle. So these two relationships that we had up there about the expectation of two independent ones and the variance of two independent ones, these relationships still apply. The difference is how you get your expectation and your variance of the variables, because it's normal random variables, we can use the normal distribution, and there's stuff in your calculator that calculates the normal distribution for you. All right, so what do we got? Let's have a look at an example. So the time taken to prepare a house for time is normally distributed with a mean of 10 hours and a standard deviation of 4. All right, so we've got two things. We've got X, which we're going to call prep, and then we got Y, and Y is going to be the painting, the actual physical painting. All right, so we got a mean here of 10, standard deviation of 4, and so our variance, don't need that last bit, scribble it out. The variance is equal to 4 squared, which is 16. Time taken to paint the house is independent of the preparation, normally distributed with a mean of 20 and a standard deviation of 3, so our variance is 3 squared, which is 9. What is the probability that the total time taken to prepare the house and paint the house is more than 35 hours? So prepare and paint. So we're wanting to know the probability of prepare and paint to be greater than 35. Right, so this is what we're going to do. We're going to combine all of these things into a third variable, which is called Z. Now, because these things here are normally distributed, then our Z will also be normally distributed. So we convert from X plus Y to Z, and Z is the standard normal. Now, normally there's a conversion factor. So normally there's a conversion factor. And so I'll write what the basic reverse conversion factor is. So to get a Z value, and Z values, we'll talk about Z values all the time related to the normal random, all right? So the Z value is what we call the standard normal. And there'll be more in that in methods. Okay, but suffice to say, you can change any normal distribution with any mean, any standard deviation into a Z value. And the Z value has a mean of 0, standard deviation of 1, and that's the standard normal. But you convert any one by using this. Whatever your value is, you take away the mean and divide it by the standard deviation. Now that's fine when you're talking about one variable, but we're here talking about X plus Y. So what in this case, our probability of X plus Y then greater than 35, we want to change that to a probability of a Z value And so when we want greater than what? Greater than, right? And that's where we use this. Now, for our particular one, what we're going to be, instead of x, what we've got is x plus y. Minus the mean, well, we need the mean, which is the expectation value of x plus y. And the standard deviation, well, in this case, we need the standard deviation of x plus y. All right, now this number x plus y, this is what we're going to use here, this 35. So 35 minus the expected value of x plus y divided by the standard deviation of x plus y. All right, so we need to know what these expectation values and standard deviations are, don't we? And so that's where that previous example that we did up here, this process here comes into it. There we go, there, that one. All right, because it's the same equations that link, even though it's the normal random, it's the same, still a random variable. So the expectation values and the variances of two independent things are still related in the same way. So let's have a look. So the expectation value of x plus y, and again it's 1x plus 1y, so that's simply the expectation value of x plus the expectation value of y, which is, get rid of that. Oh, stuff bouncing around. I don't know why it does that, but anyway, computers have their own mind somewhere. So 10 plus 2, which is 12. I think that's right, 10 plus 2, or have I read that? 20, like 20, not 2. Sorry, those people I've confused earlier. 10 plus 20, which is not 12, is 30. And our variance, of course, of x plus y. And again, 1 in front of each of those, so that's just the variance of each added together. And so I worked those out up here, 16 and 9. Which is 25. All right. Now, we need here the standard deviation of x plus y. So the standard deviation of x plus y is the square root of 25, which is 5. All right, so let me now, I'm going to rewrite this here on the next page, but I'm going to change some things. So the probability that x plus y is greater than 35 is equal to the probability that z is greater than 35 minus the mean, which was 30. All right, here we are, minus the mean, the expectation value, over the standard deviation, minus 30 over 5. There we go, which is equal to the probability that z is greater than 35 minus 30 is 5 divided by 5 is 1. Right, probability that z is greater than 1. All right, what is that? Now, this is where our calculator comes in. Because, as I said, it's the normal distribution, our calculator, and your normal distribution's used for heaps of stuff. All right, VCAR use it, ATAR use it, all right, heaps of stuff gets used for. So let's go, calculator. Menu, statistics. Let me clear all that stuff. Calc, distribution. what do I want to do? I want to calculate something to do with a distribution. Normal, PD, probability density. Now you'll notice there's a CD. We want the CD. CD means cumulative. So that means it's going to add up all this stuff. And we do want it to add up all this stuff. We want to add up to the stuff that's bigger than 1, don't we? So we choose that. And then we go next. Lower limit. What's our lower limit? So our lower limit in this case, because we've got z greater than 1, that's our lower limit, is 1. So lower limit, 1. Upper limit. All right, where do we end up? That's the question. Where do we end up? Up there somewhere. So this number that we're going to put in here is kind of a nominal number. It doesn't really matter what you do, but it just needs to be big. So I'm going to use 9,999. It's not going to make a significant difference if I add another, because remember that big tail here. So in the end, big tail down the end, there's not much going on up there. All right, very, very small probabilities when that tail gets big, right? But what we needed is to be big enough to be up into that tail bit. So any number like that. This case, the mean and the standard deviation, they're already set as 0 and 1. That's the default of the calculator. And because that's what we have used, we've created Z values, and Z values use these. So we don't need to change it. Anyway, starting to waffle. And so then I'll go next. And there is my probability. Probability is 0.586553. And it's pretty usual that you would go to 4 decimal places in this. But also make sure you do look at the exam to see precisely how many. But 4 is pretty usual for VCAR over the years. All right, waffling, and so probability at Z is greater than 1, then we've just figured that out, 0.1587. All right, so that's it. So that's the first bit, so 15A and 15B. On your work plan, the questions there. That bit that I just did with the calculator, I did cut and paste a bit off that, all right? So this is what we want to calculate, all right? So there's that. If you need that, you want to put that down in your bound reference. All right, so if you've got anything, make sure you get some help, and I know you're going to have fun with it.